Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to look at Pure Math 3, Transcendental Functions, Part 1, Logarithms and Exponentials, specifically with the laws of logarithms and then solving logarithmic and exponential equations. So first, let's go over some concepts here before we jump into the solving skills. And one of the things we want to look at is what is a transcendental function? So transcendental functions, as the word suggests, transcends or kind of rises above in some way or another. So if we look at the three different types of transcendental functions that we're going to look at in Pure Math 3, they are logarithms, exponential functions, and trigonometric functions. All three of these are in the transcendental function category. So what makes it transcendental? Well, what basically in math, what it means is that the variable x is protected in some way or another. So if you look at the exponential, the variable x is no longer written in the normal script. It is now raised up into the exponent position. And if you look at the logarithms and the trigonometric functions, the x is protected in what's called the argument of the function. So each of these sections have rules that go along with it as to how those functions operate. And you cannot use algebra from outside the function to inside the function until you first get rid of that transcendental function. So there are ways that you can cancel out the function. So when you see this, for example, if you have sine x, it's not sine times x, it's one function sine x. And the only way you can get x by itself is to get rid of that sine function. Same thing with logarithms, log x or ln x. That's not a multiplication, it is one function together, and you cannot algebraically work with that x until you get rid of that logarithmic function. So those are some of the things that we will look at as we move forward. But each of these three have a set of rules that you're allowed to use within that set. So with logarithms, we call them the laws of logarithms. And we're going to look at three laws of logarithms here in a minute. With exponential functions, they just follow exponent rules. So it's the same rules that you've learned before, except now your variable is the exponent. You're used to the variable x being the base and some number being the exponent. So, but it's the same set of rules, and so we don't have to go over that quite as much, maybe just a slight review. And with trigonometric functions, we go or use what's called identities to help work with trigonometric functions. For trigonometry, we're going to look at that later. For right now, we want to focus on logarithms and exponentials because they are opposites of each other. So just like add and subtract, multiply and divide, radicals and exponents, logarithms and exponentials are opposites. They undo each other. So as we look at, let's start here with our exponential. So our exponential is going to have some base b raised to a power x, or it can have e to the x. Now e is called the natural number. It has special properties to it. It's kind of like pi. Pi is a special value, 3.14. And I believe, if I remember right, E is 2.72. 2.71828, it rounds off to 2.72 is the value of E. And it's a special number. We don't really have time in this video to get into what makes E special, but it's got its own place on your calculator. You'll see log, and you'll see ln, L-N, L-O-G and L-N as buttons on your calculator. And then above it, you'll see the exponential. For log, you'll see base 10 with an exponent. And for ln, you'll see base E raised to an exponent. So with exponentials, we have these restrictions on the value of the base. So the base has to be greater than 0, and base cannot be 1. Well, let's take the base cannot be 1 first. Why cannot the base be 1? Well, 1 raised to any power is just 1. So instead of having an exponential curve, if you have 1 as your base, you're just going to get a straight line. So that's not very helpful. Why does base have to be greater than 0? Well, this is basically a restriction by the mathematics community because in reality, we have yet to see where a negative base or a zero base again wouldn't be helpful. 0 to any power is still 0. But there's no place in reality where a negative base has any practical use. And math, the purpose of math is to model reality. So if there's no reality that requires a negative base to model it, then we don't want to, math is already difficult enough. So we restrict the values that the base can be. So this is more or less a restriction by the mathematical community. And as such, it affects logarithms because they are opposite. So just like you can take a divide and turn it into a multiply by a fraction, same thing with exponents, they have that relationship. So in logarithms, the argument, which is what is in the parenthesis, has to be greater than 0. You cannot have a 0 or a negative for your argument for a logarithm. You can try it on your calculator and you'll get an error message. So for example, and notice I put the parentheses around the x to designate the argument. It doesn't mean that x itself cannot be 0 or negative. It's that the value of the argument cannot be 0 or negative. For example, if you have log, it doesn't really matter the base, with an argument of x plus 2, then it is possible to have an x value of 0 because 0 plus 2 is 2, which is still greater than 0. It is even possible to have an x value of negative 1 because negative 1 plus 2 is still positive 1. So it's not that x cannot be 0 or negative, it's that the argument as a whole, the value of that argument cannot be 0 or negative. So when we get into our solving process, you're going to get answers for x, 1 or 2, however many solutions for x. You need to take each of those and look back at all the arguments in the logarithms and check each one to make sure that you satisfy this requirement. Because sometimes you can algebraically get, say, 2 answers, but one of them might not work because of this rule here. So double check your solutions. As we move down, we want to see that relationship between the logarithms and the exponentials. By the way, back up here at log and ln, you have those 2 buttons on your calculator. You have logarithm, and then above that key, you have a 10 to the x. The base is 10. So If the base is 10, we call it common logarithm because we count in base 10. So we call it the common logarithm, and you don't have to write what that base value is. If there's no number written, then it's automatically a 10. Whereas if you see ln, then automatically the base is e. So ln and e to the x go together. The common log goes with base 10, and any other base needs to be written in that subscript position, whether it's a 2, a 3, a 5, whatever base that you happen to be working in gets written in that position there. So logarithms are very helpful. You probably have already run into some logarithmic scales and maybe you didn't even realize it. For example, the Richter scale for the size of earthquakes is a logarithmic scale. In other words, every value is a power of 10. Same thing with the best decibel scale for loudness is a logarithmic scale. I believe the luminescence scale is also a logarithmic scale for brightness of light. You also use logarithms in chemistry with in working with pH. The power of hydrogen is a logarithmic scale when you compare the power of hydrogen with the power of hydroxide. So there's many places, especially in science, where logarithms are used, and the fact that you can translate it into an exponential can also be helpful because you are already used to exponential rules. Okay? So this is how you transfer it from a logarithmic function into an exponential function. If you start with y equals log to whatever base of the argument x, then what you do is notice the b is your base raised to the exponent equals the argument. The base raised to the exponent equals the argument. So what that means is your answer to a logarithm is an exponent. That's an important conceptual thing to remember. Your answer to a logarithm is an exponent. So your base raised to the power, raised to the exponent, equals the argument. So the argument is what you get as the answer to the exponential function. This b raised to the y power equals the argument that was in the logarithm. So you should be able to convert this back and forth. So maybe a quick example, if you have log 2(8) equals 3, is the same thing as 2 to the third power equals 8. The base to the exponent equals the argument. 2 cubed equals 8, and you should be able to make it go back and forth like that. So this is a very helpful for you to be able to convert into whichever form that is helpful for your solving process. Now, you already know the exponent rules. When you have like bases and you're multiplying like bases, you add exponents. When you are dividing like bases, you subtract exponents. And when you have an exponent raised to another exponent, you multiply the exponents. So there are other exponent rules, but if you know the exponent rules, then you can think backwards to the logarithmic rules, your laws of logarithms. So your first law of logarithms is if you have a logarithm of whatever base, and inside the argument you have a product of values, then remember when you have like base, When you're multiplying like base, you add exponents. And remember, the answer to a logarithm is an exponent. So when you're multiplying with a like base, you add the exponents. So log of base b of m times n, the product in the argument becomes log base of the argument m plus log to the same base of argument n. The second law of logarithms follows our division rule. When you divide like bases, you subtract exponents. So when you have log base b of m divided by n, so you have a quotient or a dividing problem values in the argument, then you have log base b m minus log base b n. Then when you have an exponent raised to an exponent, you multiply. Okay, so remember your logarithm, the answer to a logarithm is your exponent. And when you have an exponent raised to an exponent, you multiply. So if you have a logarithm where your argument can be changed into some exponent form, the exponent then multiplies to the front of that logarithm, n log base b times m. These three laws of logarithms, there are more. Some curriculum go off into like 6 different laws of logarithms that you can derive, but these are the main 3. And they are also reversible, meaning you can go either direction. So if you go in the direction that we just discussed, it's called expanding. If you put them together, it's called condensing. So maybe you need to condense the logarithmic statement into one logarithm, or you might want to expand the logarithm into its various parts. So these are three very important laws that help you get around and manipulate the logarithmic setting. And your exponent rules is what helps you to navigate exponentials. And so let's look at a couple of examples where how the opposites work to cancel out. Obviously, when you get into a solving situation, you have to cancel. For example, if you have 3 times x, you have to divide by 3 to make the 3's cancel. So how does that work with logarithms and exponents? So up here, we have 2 different examples of exponentials. Y equals e to the x and y equals just any base to the x. So what you want to do to cancel an exponential, you need to do the logarithm of the same base to both sides. That is if you want to cancel it. You can actually do any logarithm to both sides, and if it's of a different base, it won't cancel. You're like, what are you saying? Well, look here, y equals e to the x. Now, in the Cambridge question solving process, usually we're going to end up using ln. I'm not saying we'll never use other logarithms, but the ln x is going to be the most frequently used. So if we have y equals e to the x, we ln both sides. So now we have ln y. So the y becomes the argument of the logarithm. It is not multiplication. It is not ln times y. It is ln y. Y is now the argument of this logarithm. And then we have ln e to the x. Well, the base of ln is e, and the base of the exponential is e. So if those bases are the same, then it cancels. Okay, so it cancels. Over here, the base was y, and the base of ln is e. They don't cancel. Here the base is e and the exponential base is e. They do cancel. And so we end up with ln y equals x. So if the logarithm and base cancel, the exponent then drops down to your normal script. Here we have y equals b to the x. So if we ln both sides, we have ln y equals ln b to the x. Neither cancels because the base of ln is e, and we have y as a base on the left and b as a base on the right. So it doesn't cancel, but we can use our third law of logarithms to take that exponent and multiply it to the front. So ln y equals x ln b. Now, if b is just a number, then ln b actually becomes the coefficient of your variable x. Ln y equals ln b times x. This is now multiplication. So the ln b would become, as you calculate it, you get some decimal, that would be the coefficient of your variable x. On the other hand, if we're starting with logarithms, and I have two here, y equals ln x, so we have the natural logarithm, and we have y equals log to any base x, and we want to get rid of the logarithm. Well, the opposite of a logarithm is an exponential. So this process is called exponentiating both sides, meaning both sides are raised up as the exponent to the base. So for this one, I exponentiated both sides to base e. So you have e raised to the y power equals e raised to the ln x. Notice the e and the ln have the same base, so they cancel, and the argument drops down to your normal script line. So you have e to the y equals x. Over here, we have any particular logarithm, and so we raise both sides to base b, could be any number. Okay, so whatever this base is, we exponentiate both sides to base b. So now we have b raised to the y equals b raised to the log bx. Notice the base b and the log b are the same number, and as long as they are the same number, they will cancel out, and again your x drops down to the normal script. So we have b to the y equals x. So that b can be any constant, 2, 5, 8, whatever. Okay, so this is the rules and the concepts that you need for logarithmic and exponential equations to solve those equations. So now we're going to get into the examples. So let me set up the board for our first example. Okay, let's look at our first example here. Just before we look at our first example, I thought of another application of logarithms. We talked about different things in science, like Richter scale, chemistry, you have the pH scale, but also in biology, you have population growth. Whether it's human population growth or bacterial population growth, that follows exponential curves. So where we talked about the examples for logarithms, population growth is an example, and also compound interest, if you want to throw compound interest in there. Those, any kind of growth and decay model, those are exponential models. So the exponentials and logarithms have a lot of practical applications. So it's really important that you can get these transcendental functions down so that it helps you to work with those other applications. So let's look at our first solving example here. Here's the desk. You can look at the code up here if you're interested in what past paper it came from. It says, showing all necessary working solve the equation 9 to the x equals 3 to the x plus 12. Give your answer correct to 2 decimal places. So let's go back to the board. Here we have 9 to the x equals 3 to the x plus 12. Now, one very important thing that you need to remember with both exponentials and the arguments of logarithms is you can reshape any particular number into a base and an exponent, and especially if you see a common base. So here we see the number 3 and the number 9. They both have a common base of 3, or we can change 9 into base 3. 9 is the same thing as 3 squared. So that is going to become a very helpful ability, is for you to recognize when you can take two numbers and convert them into the same base. Now 12, even though 12 has a factor of 3, 12 cannot be converted into base 3. In other words, 3 squared is 9, 3 cubed is 27, but we don't get a 12 from base 3 unless we use decimals, and obviously we can't bring that to our mind. So what we want to do here is write this as 3 squared to the x equals 3 to the x plus 12. And now you know your exponent rules. When you have an exponent raised to an exponent, you multiply. So this becomes 3 to the 2x, and I'm going to move these all over to one side. So minus 3 to the x minus 12 equals 0. Okay. Now, if you remember in Pure Maths 1, we covered a video on the topic of reducing to a quadratic. And this is really an example of reducing to a quadratic. So you might want to go back to that Pure Maths 1 video on reducing to a quadratic if you need help. But you should recognize this as a quadratic. Notice it follows the pattern 2, 1, 0, or a multiple, any multiple of that 2, 1, 0 pattern, where you have a squared, a regular, a first power, and a 0. So if you look at it this way, this 3 to the x is really acts like a variable in itself. It's a unit. So this one here is really a 3x squared. So it's like y squared minus y minus 12. You could actually use the method that we did in reducing to a quadratic back in Pure Maths 1. So you need to recognize that. However, for this one, I'm just going to go ahead and factor it. We don't really need to the purpose of that reducing to a quadratic in Pure Maths 1 is to use the quadratic formula, which you could use, but you don't need to because this factors. What you're looking for are the factors of 12, 1 and 12, 2 and 6, 3 and 4. That subtract to give you a 1. Now this is the tricky part right here. It says that's a 3. Okay, let's take a timeout for just a second and let's analyze this 3 to the x. Remember, this 3 to the x is like a unit. Okay, it goes together. It's a transcendental function. We haven't broken it apart. So right now it's one unit. That means the coefficient is actually a 1. So you can have exponentials with coefficients in the front. You can have 1, you can have 2, you can have 5. It tells you how many of these units that you have. You have 2 units of 3 to the x, or 5 units of 3 to the x. So if you have a coefficient, it's multiplied out to the front. You cannot multiply 2 times 3. Okay, remember your normal algebraic rules don't apply from outside the function to inside the function until you first get rid of that transcendental function. You'd have to get rid of that base 3 first. So this is how coefficients work. So if you're looking at a general form, it would be a times b to the x, where a is the coefficient, and then your b to the x is the exponential part. Okay, so that's a very important thing. Some students get confused and they either want to multiply that number in, or they don't recognize what the coefficient is in the first place. So be careful with that. So when we come back here, the coefficient on this is 1. So we want 3 minus 4 to get that -1. So this is a 3 to the x, and we want a minus 4 and a 3 to the x plus 3 equals 0. Let's just check this out. When we multiply 3 to the x times 3 to the x, when you multiply like bases, you add exponents. X plus x is 2x. -4 times 3 is -12. We have a -4, 3 to the x, and we have a +3, 3 to the x. So remember, those are the coefficients, and so that gives us a -1, 3 to the x, which is just -3 to the x, which is what we have here. Okay, so it's important to understand how that works so that your mechanics are correct. Now, just like in algebra, we solve these, each factor equal to 0. So we have 3 to the x equals 4, and we have 3 to the x equals -3. When we set these equal to 0, subtract 3, add the 4. And at this point, you need to remember your restrictions. Base exponentials cannot be 0 or negative. So this one is going to cancel. In other words, there's no value of x that you can raise a positive base to and get a negative number. Okay, so 3 to the 1 is 3. 3 to the 0 is 1. 3 to the 1/2 is √3. 3 squared is 9. No matter what kind of exponent you put on it, even if the exponent is negative, 3 to the -1 is 1/3. So regardless of what you put up there as an exponent, you're always going to get a value greater than 0. So if you have an equation and it's 0 or less, you're going to throw it out. Okay? Then we get this one. So now we're ready to undo our exponential base here. We have a base 3. So what we're going to do is we're going to log with base 3. So it's going to look like this. Log base 3 of 3 to the x equals log base 3 of 4. On this side, the bases of the exponential and of our logarithm are the same. So it cancels out, leaving x. And then what you're looking for is to plug this into your calculator. On your calculator, you'll have a log button that looks like this, where you'll plug in the 3 and the 4. If you don't have a button like that on your calculator, let me show you really quick. When we put it, looks like this on the calculator. It's over here in the far corner, the button over here, and it gives you this look when you look at it in the calculator, and all you have to do is enter the values. If you do not have that button on your calculator, then you can do what's called the change of base. You can either use your logarithm button or the ln button. It doesn't matter, but just use one or the other. And so you can convert this into log. So this would be your base 10 on your calculator of the big value, that is the 4, over log of the little value, which is your 3. So it'd be log 4 over log 3. And you can also use ln 4 over ln 3. So this is called a change of base. You're changing it from base 3 into either base 10 or base e. And the thing with logarithms is they are proportional. So it doesn't matter what base that you're in, they will be proportional to each other. So log 10 over log 10, log 4 over log 3, or ln 4 over ln 3, if you don't have this calculator button here. If you have this one here, all you have to do is type in the 4 into the big box and the 3 into the little box. You'll fill the little box in first and then the big box. Okay? And when you do that, you get a value of 1.26. Said the 2 decimal places. So 1.26 is the value. You can check on your own calculator to make sure that you're doing it right. And you can also try these if you want to show that those work as well. So that's our first example. And let me set up the next one. Okay, let's look at our second one here. Pull it up on the screen so you can see it. Here's the code up here from Winter 19, paper 33, number 3. Showing all necessary workings, solve the equation 3 to the 2x plus 3 to the negative x all over 3 to the 2x minus 3 to the negative x equals 4. Give your answer correct to 3 decimal places. So let's go back to the board. And remember, we're dealing with exponentials. You follow exponential rules as you work through this, but we can also use the algebra on the outside of our exponential functions. So the first thing I notice is we have a fraction. So we want to multiply by the denominator to make this disappear. So this is going to become 3 to the 2x plus 3 to the negative x equals 4 times 3 to the 2x minus 3 to the negative x. And when we distribute the 4 through, we get 3 to the 2x plus 3 to the negative x equals 4 times 3 to the 2x. Notice the 4 does not get multiplied by the 3. Your 3 to the 2x is your exponential. So that multiplication has to stay on the outside. Now the 4 is functioning as the coefficient to the exponential. And then when we multiply over here, we get minus 4 times 3 to the negative x. Again, the 4 does not multiply the 3. The 3 is part of an exponential, and the 4 just becomes the coefficient. So now we have this, and notice these negative exponents. Sorry, this is not a 1, this is a negative x. And so this is the same thing as 3 to the negative x is the same thing as 1 over 3 to the x. Okay, remember your negative exponent rule, it moves it below the division bar, or from below the division bar to above the division bar. So you have 1 over 3 to the x. So we have fractions in this equation. So we're going to multiply everything by 3 to the x to make this cancel. Notice if we multiply by 3 to the x, it will cancel those. So when we multiply this on this side, 3 to the x times 3 to the 2x becomes 3 to the 3x. When you multiply, you add exponents. Here, when you multiply, you add exponents. X plus negative x becomes 0. And so that cancels and just gives us a 1. Okay, so this times this, x plus negative x is 0. 3 to the 0 is 1. Times here, we get a 4 times 3 to the 3x minus 4, because this again cancels out and just leaves us with the 4. Now we want to combine like terms. So we want to get our 3 to the 3x's on the same side. So we're going to subtract it this way, and we're going to add the 4. So we'll add the 4 to both sides, and we will subtract our 3 to the 3x. So over here we get 5, and over here 4 minus 1 is now 3 times 3 to the 3x. So make sure you keep the coefficients separate in your mind from the exponential, the base and its exponent. Now we can divide by 3 because this is connected by multiply. It is outside the exponential, so anything outside the exponential still can use our normal algebra. It's just within the exponential, we have to follow the exponent rules. So we divide by 3, so we're going to end up with 3 to the 3x equals 5/3. Now we want to get rid of our base 3. We're now ready to break apart this exponential so that we can get to our variable. So we're going to log base 3 to both sides. So this is going to become log 3 to the 3x equals log 3 5/3. On this side, it cancels, leaving us with just 3x. And when you put in log 3 to the 5/3, you get 0.46497. 0.46497. When you enter this into your logarithm button that we just talked about earlier. And now we need to get x by itself. So we're going to divide by 3, and we get x equals 0.155 to the 3 decimal places that it asked. X equals 0.155. So there are 2 examples on how to solve exponential equations. Now we want to look at a couple of examples of how to solve logarithmic equations. Okay, let's look at what we have here. Now we have an logarithmic equation given that ln of 1 plus e to the 2y. So not only do we have a logarithmic equation, we have an e on the inside, exponential on the inside of the argument. So ln of the argument is 1 plus e to the 2y equals x, express y in terms of x. In other words, right now, x is the subject, and they want us to rearrange it to make y the subject. So let's come back to the board so we have room to work. So this is what we have. We want to get y to be the subject. That means we have to break apart all these other things that are attached to the y. And so the first thing that we need to break apart is this transcendental function, this logarithm. And the opposite of a ln is base e. So we're going to exponentiate both sides base e. Both sides get lifted up as exponents. What you do to one side, you have to do to the other. The ln cancels. It leaves us with 1 plus e to the 2y equals e to the x. So now we can subtract 1 from both sides. E to the 2y equals e to the x minus 1. And now to get rid of an e, we're going to ln both sides. So we get ln of e to the 2y equals ln of e to the x minus 1. So we ln both sides. And on this side, our ln base e and the exponential base e cancel. So that gives us 2y equals ln e to the x minus 1. This does not cancel because it is not, this one doesn't cancel because of this minus 1. You have to ln the whole side. So notice if you were just lawning e to the x, that would cancel to give you the x. But we're lawning the whole side, ln of e to the x minus 1. This does not cancel, so be careful with that. If your ln is of an individual term with the same base, it cancels. But if it's connected by plus or minus, logarithms do not distribute across add and subtract like that. So you cannot cancel that out. And so now you just divide both sides by 2. And so we end up with y equals, there's y as our subject, 1/2, we can put that in the front, ln of e to the x minus 1. And that then is our equation made with y as the subject. Okay. Now, we didn't actually solve for a value. This one was more of a manipulation that used both exponentials and logarithms to get from x being the subject to y being the subject, but very helpful in your understanding of how to get rid of one or the other. I'll set up for one more where we actually solve in logarithmic equations. Okay, let's look at our last question here for this video on solving logarithmic equations. Again, up here's the code if you're interested. Showing all necessary workings, solve the equation ln of 2x minus 3 equals 2 ln x minus ln with the argument of x minus 1. Notice all of these logarithms have the same base. Give your answer correct to 2 decimal places. So when you have a logarithmic equation with multiple logarithms, usually you want to condense it. That is, put them together so that you have one logarithm on one side and one logarithm on the other side. So we're going to use our laws of logarithms. The first law that we're going to notice is this 2 can become the exponent of our argument x. So this now is ln 2x minus 3 equals ln of x squared minus ln of x minus 1. Okay, so this was the third law of logarithms. Now we want to use the second law of logarithms. When you have a subtraction, that means you can condense it into one logarithm where your argument is in the division form. So this becomes ln of 2x minus 3 equals ln of x squared divided by x minus 1. So remember, when you divide like bases, you subtract exponents. And the answer to a logarithm is an exponent. So we have 2 exponents being subtracted. That means that they were in division form as the exponential. Okay, so now that we have it condensed with one log on one side and one on the other, now we can cancel out those logarithms a little bit easier. And so we're going to exponentiate both sides to base e, because our base of ln is e. So we exponentiate both sides to e, and that cancels, and that leaves us with 2x minus 3 equals x squared over x minus 1. Now we're just down to algebra now. So we're going to multiply both sides by x minus 1. And that's going to give us 2x squared minus 2x minus 3x is minus 5x plus 3 equals, this cancels x squared, subtract x squared, so we get x squared minus 5x plus 3 equals 0. And you'll probably notice that you cannot factor 3 to give us a 5. So you're going to have to use the quadratic formula. So when you solve this you're going to get two answers. You're going to get x equals 0.70. You're going to get x equals 4.30. We're going to two decimal places. So use your quadratic formula if you have forgotten. X equals negative b plus or minus root b squared minus 4ac all over 2a. By now you should have that memorized. It is, by the way, in the Cambridge formula sheet. I believe, or at least it was in the old one. I can't remember if it's in the new one or not. The old version used to have it, but you should have it memorized regardless. So you get these two answers, but remember I said that logarithms, the arguments have a restriction. The argument cannot be 0 or negative. You say, well, both of these are positive values. It's not about the value of x, it's about the value of the argument. So if we go back to the original and we put our 4.30 in, well, 4.3, let's just take 4 times 2 is 8, 8 minus 3 is 5, no problem. Here, x, you put in 4.3, no problem. 4 minus 1, that's 3, no problem. Okay, so this one is fine. What about the 0.7? Well, if we have 2 times 0.7, that's 1.4. 1.4 minus 3, uh-oh, that's negative. If we put 0.70 here, it passes here. And if we put 0.7 here, 0.7 minus 1 is negative 0.3. So if it fails any one of those logarithms, then you have to throw out the answer. Because if you tried to plug it in on your calculator back into the original equation, you're going to get error message. So you need to recognize that the 0.7 does not work and you need to throw it out. The only answer that you should have is x equals 4.3. And the easiest place to recognize it is right here. 0.7 minus 1 is going to give you a negative. So be careful of that. Always double check your answers when you're solving logarithmic equations. And you have to look at every argument. And remember, you're not looking at the value of x. You're looking at what the argument total value comes out to. So there we are at the end of our first video for logarithms and exponentials. If you come back for part 2, we'll talk about graphing. We'll talk about modeling with logarithms particularly, or exponentials. And we'll look at the derivatives and integrals of these functions. So thank you for joining me. I hope it was helpful for you. Hope to see you again next time in the Zoom room.